less. All right, so I've drawn a circuit on the board, and this is called an LC circuit. We have a battery and a switch, of course, but other than that, we have an inductor and a capacitor. And what we're going to do is we're going to start out by flipping the switch to position A. And so effectively, we have just a single loop here with a battery and a capacitor and an inductor that does nothing. It's cut off from the circuit, so nothing's going to be happening here. We could just delete that with no effect. Now, what's going to happen is this capacitor is very quickly going to become charged. And I say very quickly because normally, charging a capacitor, there's a delay due to the time constant, which depends on the resistance. But we didn't put a resistor in this circuit. So there's always going to be a resistance. We've got, the wires themselves. But effectively, we're going to very rapidly build up a charge on the capacitor. Now, even if we say replace the wires with superconducting wires, so the resistance was zero, completely just zero in the wires, there's still a battery that has internal resistance. But anyways, we're going to very quickly build up a charge on the capacitor. Now we'll build up a charge, say Q max. And then what we're going to do is flip the switch to position B. And so now we have a loop where the charge is going to want to go, from the positive plate to the negative plate. Now, if there was no inductor here, not much would happen. This charge would just, the capacitor would very quickly discharge. Like if you take an actual capacitor and just have one wire touch one end each terminal, the capacitor is discharged. You don't really have to wait for it. It happens so quickly because there's so little resistance in the wire. But in this case, we have an inductor. So we have this initial current here. I'm going to call this I0. That's going to flow through the inductor, and that's going to bring charge from the positive plate to the negative plate. But again, we can't have this happen instantaneously. Because if we have a large current, we initially had a current of 0 before we flipped the switch. And now that we flipped it, we're going to build up a current. And the more rapidly we try to do that, the greater the back EMF due to the inductor is going to be. And so, we'll initially get a current that's going to flow through and deliver a positive charge to the negatively charged plate, which will lower the charge on the capacitor. We're removing positive charges here, which will cancel out the negative charges on the capacitor. And, of course, that will take some time, but eventually the capacitor will become discharged. So, we have no charge on the capacitor, at least momentarily. However, we still have a current. The current's going to, vary with time, but there's still a current here. And so this current is going to start delivering positive charge to the bottom plate, which will result in negative charges accumulating on the top plate. And so if we look at the current, it rises up, and once the capacitor is discharged, we're at our maximum current. So if we were to plot the current as a function of time, it would rise. So it starts at 0, it would rise and reach its maximum value. And then once it's at its maximum value, that's when the capacitor is discharged. And so now that we're putting positive charges on this plate, that's fighting this current. And so the current is going to start to decrease. And again, that's when the inductor kicks in, because if the current's decreasing, then the inductor is going to want to oppose that decrease in the current. And so the inductor is going to continue to drive this current, and ultimately we're going to end up with the same amount of charge on the bottom plate. So initially we started out with a certain charge on the top plate. That charge, let's call it Q max, would just be the capacitance times the EMF of the battery. So that started out on the positive plate, or the top plate is positive charge, Q max negative charge on the bottom plate, and now the situation is reversed. And we know that has to be the case by conservation of energy, because we're assuming that there's no resistance in the circuit. It's kind of an idealized circuit. And so initially, after we charge up the capacitor, flipping the switch to A, there was energy stored in the electric field of the capacitor. And as the capacitor is discharging, the capacitor is losing energy. But we're building up a current, and we know that currents carry energy as well. Magnetic fields store energy as well. So we have this magnetic field in the solenoid, or just the inductor in general, that so the energy is transferring from the electric fields to the magnetic fields. And once a capacitor is discharged, initially all the energy was in the electric field. Once the capacitor is discharged, it has no electric field anymore. There's no electrical energy, so all the energy has to be magnetic. And this is going to continue driving this charge until the current becomes zero, in which case the energy transfers back to the capacitor. So it's this energy just going back and forth between the capacitor and the inductor, and with no resistance, the total amount is going to remain constant. So if we had Q max, positive and negative, eventually we're going to end up with Q max where the positive is on the negative, and the negative, or the top plate, I don't know if what I said actually made sense. The positive charge is going to be on the bottom terminal in the capacitor, and the negative charge will be on the top. But it'll reach that same value, Q max. So the current is going to go up and down. And then it's going to, actually, bad picture. The current's going to look something like this so far. So we're looking at, say, the current as a function of time. So initially it was 0. It rises up to a maximum value here, and that's when the capacitor is discharged. And so all the energy is stored in the inductor, and then the current drops to 0. And now we're kind of in the same situation we were when we started, except the charges are reversed. So what's going to happen is the exact same thing. Initially we had positive and negative charges, on the top and bottom. When we flip the switch, the positive charge flows around, and now we're just the same amount of charge, but now the situation is reversed. And so it's going to behave in the exact same way. It's just a loop. It doesn't care what direction it's going. And so now the current is going to reverse direction and flow this way. Back to so we'll go back to our starting point, and it's going to go through in exactly the same way. And so we're going to end up with a current that looks like this, at least over one complete cycle. Once we're here, this is a period. We're back to our starting condition, and then it's going to just keep on repeating itself. because there's no energy lost. So the charge is just going to go back and forth from the top to the bottom plate and then back to the top. The energy is going to transfer between the electric field and the magnetic field. And with no resistance, it just keeps on oscillating forever if there's really no resistance. Well, I shouldn't say forever because there could be electromagnetic radiation emitted, which would dissipate energy. But, yeah. So, as long as we ignore resistance and other forms of energy loss, it's just going to keep on cycling. And what we want to do, we want to know how fast this is going to be cycling. So, we're going to look at this in terms of energy. And conservation of energy, the only two sources we're considering, and for the purpose of this topic, we're saying these are the only sources that are significant. We have electrical energy and magnetic. Energy stored in the electric fields and energy stored in the magnetic fields. And so whatever energy we lose in the electric field goes into the magnetic field and vice versa. So we can say that change, it's potential energy. So the change in energy in the electric field plus a change in the magnetic field equals 0. If you look over like a quarter of a cycle, whatever energy was stored on the capacitor, that goes to 0. So delta E for the electric field would be negative, whatever the maximum energy is, and then delta U for the magnetic field would have to be numerically the same. So they add up to 0. So it's just a transfer of energy. Now, the energy in an electric field is we talked about the energy stored in a capacitor. That would be Q squared over 2C. And the energy in an inductor, so that would be, in an inductor, that energy would be stored in the magnetic fields. That is 1/2 Li squared. So these are the kinds of the potential energy in the electric and magnetic fields. And we want to basically solve this equation now. So let's consider just an infinitesimal time interval. We can say we can replace these with dE dt or du dt. So we have these changes are equal to 0. We add them up. So let's do this. Now, these are time derivatives, so we have to be a little careful here. Let's differentiate this term with respect to time. So Q depends on time. So the derivative of Q squared is 2Q. So we have 2Q over 2C. However, that's just differentiating Q with respect to, or differentiating Q squared with respect to Q. But Q is a function of time. So because we're differentiating with respect to time, we have to use the chain rule. So we have just differentiating Q squared, that gives us a 2Q with a constant in front, but then the chain rule, plus or times dq dt. And then for the magnetic field, again, L is a constant, so I is a variable. So again, the derivative of I squared is 2I. So I'm just going to cancel out the 1/2. So here, bring the 2 down, we have Li, but again, I is a function of time, so we have to use the chain rule here. And I think what I'm going to do is just, get the equation here, and then we will, erase the board and write it down again. But I'll write down one more thing over here. So the current is the time derivative of charge. And so here, dq dt is I. And so let's factor an I out of this equation. So here we've got an I here. So basically, I'm going to write it this way. Okay, so the first term, here's our I, which we factored out. So we have 2q over 2c, or I took the constant out, 1 over c times q. And now if we factor an I out of this term, we have L di dt. But I is dq dt. So di dt is the second derivative of charge with respect to time. So here we have L. Now I'm going to use a particular notation. Or I put 2 dots above it. Very common notation, like say f dash would be like df dx. But a very common notation, again, it's not necessary to do this, but if you are, specifically if you are taking a time derivative, then instead of a dash, you can use a dot. So like f dot would be df dt. So q, so in that notation, I is equal to q dot, and di dt would be q dot dot, the second derivative of q. Now the downside of this notation is we could write this as I dot, because di dt is just the time derivative of I. So we could have written down I dot, but that is very easy not to notice, because I is normally dotted by itself. But, yeah. Okay, now, so yeah, I just left it over there as di dt. Okay, so now we have a product of 2 things that equals 0. Now the current is going to look something like this. So there will be moments when current is equal to 0, but it's not identically equal to 0. The current is not typically equal to 0. And so then this term in parentheses has to equal 0. So what I'm going to do is erase all of this. So let's set the term in parentheses equal to 0, but what I'm going to do is rewrite it. So we have q dot dot, that's the second time derivative. So basically what I'm doing is dividing by L to get that by itself. And there we go. So this is our differential equation. And we should expect it to, let's also write down our initial condition that Q0 equals Q max. Kind of want to keep that picture if there's room for it. Okay, because we had the switch in position A, and then we flip it to B, when our capacitor is at its maximum charge. So we should start with our maximum charge. All right, and now what we want to do is solve this equation. There's various ways to do this. One is, if you remember simple harmonic motion, like a mass on a spring, basically we had x dot dot plus, if you just start with a mass on a spring and apply Newton's second law, force is minus kx, set that equal to mass times acceleration, where this is acceleration, the second derivative of position with respect to time. And basically, these two equations are identical. The letters are different, but the relation between these variables is exactly the same. And so mathematically, these two equations are identical, and so they have to have the same solution. So you could try to relate this to a mass on a spring. However, this equation is easy enough to just solve on its own, just kind of by inspection. So if we look at, let's do one thing then. Let's define omega squared to be 1 over LC. So then we have Q dot dot plus omega squared Q equals 0. Now, we're looking for Q as a function of time. And so basically what we're doing, let's start with something a little bit easier. Or let's go with x. Say x is a variable, then x dot dot plus x equals 0. We can just kind of look at it and say, I know a solution to this. X is equal to, say, sine of t. Then x dot would be cosine omega t, or cosine of t, and x dot dot is minus sine of t. So, we have a variable, and we add to that variable its second derivative and get 0. So basically, if we take the second derivative, we get minus what we started with. So we have x dot dot equals x, or x dot dot minus x. Sorry, there was a minus sign there. I wrote that wrong. I think I forgot to write the equal sign, actually. So what we have here is x dot dot minus x equals 0, or just rewriting it. And so basically we're taking something and we're looking for a solution that's either a sine or a cosine, because cosine would work just as well. However, in this particular case, we want a solution that looks like a cosine, because cosine of 0 is 1, and we know that we're starting out where Q is equal to Q max. So if we were to write Q is equal to, say, some constant times sine omega t, well, this can't work with our initial conditions, because then if we look at Q0, sine of 0 is 0. So this equation would solve this equation, but not with the right starting condition. Now, in general, a more general solution to this equation, like let's go back to our simple one. We could say x is sine t. We could say cosine t as well. If you take the derivative of cosine, you get minus sine, and then the derivative again is minus cosine. So that works. More generally, you could say x is equal to a. You could do cosine or sine. It's a cosine of t plus some constant, which is called phi. That's the phase constant, or the phase shift. And this works as well. And again, you could just have cosine of t plus phi. If you put an a in there, that doesn't change anything. And generally speaking, we have a second order differential equation, so we should expect to have two constants. However, in this case, we're just going to do a straight cosine, because we started with our maximum charge on the capacitor. So let's do this. So say Q equals Q max cosine omega t. And that works. So if we do Q dot, we take the derivative of this. Derivative of cosine is minus sine. And then we're differentiating with respect to time. And because our argument is omega t, we have to use the chain rule and pull out an omega. So derivative of cosine gives us a minus. The chain rule gives us an omega. And then we have Q max sine omega t. And then taking the second derivative, derivative of sine is going to give us cosine. So we still have that minus sign there. That doesn't change. The chain rule is going to give us another factor of omega. And derivative of sine is cosine. And notice that this here, Q max cosine omega t, that's just Q. So we have Q dot dot minus omega squared, or Q dot dot equals minus omega squared Q, which is this equation. If we just move this term to the other side, we have Q dot dot plus omega squared. Replace all that with Q. And we can see that this is a solution to our problem with the right initial condition. So now if we plug in Q0, cosine of 0 is 1, so we get our maximum. We just get Q equals Q max to begin with. And we know Q max is C epsilon. So I'm going to erase this. I was just checking to see if this worked. Generally speaking, you want to solve a differential equation. The first step is to try to guess the answer and just check and see if it works. Usually you want to kind of think about what the answer should look like and then guess it and check it. And even if it's not right, maybe you'll get close and see how to fix what you initially tried. And a lot of differential equation solving is just trial and error. Okay, but now that we're at this, let's take the derivative. The current is just dq dt, or q dot. And so if we take the derivative with respect to time of this cosine is going to give us a minus, and derivative of cosine is sine. The chain rule is going to bring out a minus. So the current as a function of time is minus Q max omega, or minus I max sine omega t, where the maximum current is Q max omega. All right, now this minus sign, notice that we kind of just argued that the current should look like this. It should rise up to its maximum value and then drop. And again, this is like right here on the graph. The charge went all the way from positive to negative, like the polarity of the capacitor just reversed itself here. And so then it's going to flip back the other way. So we're at the half cycle. Current goes back to 0. And then it goes this way. So it becomes negative. So the only difference from what we kind of argued the current should look like is this minus sign. And yeah, we could have put that in the beginning. I was just thinking of the magnitude of the current at first. But initially, like when we flip the switch to A, we have a current going clockwise. And then at t equals 0, we have a current going counterclockwise. So it makes sense that this minus sign here is here. That just means the current is initially going counterclockwise in the circuit. Okay, so that's an LC circuit. Not 100% realistic because we're assuming that this energy is just going to flow back and forth between the capacitor and the inductor indefinitely, where in the real world energy would be lost to resistance or things like radiation. But yeah, we found the current and the charge on the capacitor as functions of time. So I think that'll be it for this topic. And then later we'll look at what effect resistance has on that circuit. But that'll be it for now.